Hello and welcome to Unit 4 again. Today we'll be looking at the second lab in this unit, which is section 4.2, exploring the data, in other words, exploratory data analysis, also abbreviated as EDA. Let's read on our Jupyter notebook just to make sure that all of the imports and the data has been loaded. So a quick recap: we're importing pandas, numpy, matplotlib, and seaborn. These will be used as and when over the course of this unit. We'll be looking at bike sharing dataset again. We'll work through this dataset to the end of the unit and then pick up the other dataset that we selected for classification and run it through the unit again in one go. So bike sharing dataset has two options. We can either use the day.csv or we can use hour.csv. In this case, we're looking at the day data. We can always look at the hourly data once we get through the exploratory analysis. So running this again, we see the first 5 rows because by default head function on a data frame, on a pandas data frame, will bring you the first 5. You can actually change that, let's say, to the first 9, and you'll see 0 to 8. It says 0 indexed, so that's 9. In fact, you can see the record index under instant column or attribute, which is going up until 9. You can also take a look at the last 9 rows. For instance, we change the head function to the tail function. This is going to give us the final 9 rows of the data frame instead. As you can see here, from 723rd record to the 731st instance, which is the final instance in the data frame. From the previous lesson, we recall that we have a range index of 731 entries. Let's run this again. 731 entries, the description, the different attributes and features in there, what's the descriptive stats of each of those numerical features. We checked the is null, there were no nulls here. The shape is giving us 731 records and 16 features. The number of unique instances in each feature is also we checked. So this brings us to exploratory data analysis on this data set. So let's say we want to visualize the bike rental data or bike rental demand data over time. We know that the date column in this data frame is called DTE day. And I mentioned to you in the previous lab that we could actually convert this to a data type. Quick recall just to jog our memories. We have DTE day as the second column of our data frame data. This is non-null. It's got 731 entries, and it has automatically been ingested as an object when we loaded the data using pandas.read CSV, read_CSV. We could also give data types when you are loading CSV files here, but since we've already loaded it, let's change the data type by actually using pandas2_datetime and giving it the column in our data frame. This gets loaded into a new column that we're calling datetime. That's part of the data frame. So if you want to create a new column, all you have to do is call the data frame and within square brackets a new name of that column, and then it could be a copy of a previous column or some kind of a transformed or processed version of the column. In this case, we're converting DTE day from an object data type to a datetime data type. We also use datetime to set the index. So now we actually have the date for each record. We know that 731 days exist in our data set that spans 2011 and 2012. And we're saying that this is in place. So actually that column will be converted into the index. And this means that the column will no longer exist in the data frame as a column, but it will be available as the index. We use PLT, which is our alias up there for matplotlib.pyplot. So PLT is for pyplot, which is part of matplotlib. We call the figure function, giving it a figure size of 15 by 5, so that's more horizontally stretched. We use plt.plot, taking the count column from the data frame, the count of both casual and registered riders that are renting these bikes. We give it the label bike rentals, which could be anything. This is what we see here in the legend. The title of the plot, which is given using plt.title. We also give labels to the x and y axis by using x label and y label functions. Here we call the x label or x axis date, because it is the date column, which is our index, the date time column that we set as the index of the date frame. That's automatically picked up. And the y label or the y-axis is called number of rentals, because we're giving it CNT, which is our count column. We say that we want to show the legend and we want to show the plot. Even if we didn't do this, we could do away with these and it would still give us the same output, except that you see that we don't have the legend here. plt.show is not really necessary in Jupyter notebooks, but if you're building in an IDE or let's say a text editor like Sublime, you do have to call plt.show for the plot to pop up. So let's put the legend back and just get rid of the plt.show call. So coming to the visualization of the actual data, we can see lots of peaks and troughs, and we can see some trends, as you see from about early in the year in 2011, we have an uptrend, and this uptrend continues up until about summer, so mid-year, around June, July time, and then we see a downtrend here. And the next year, plot trend reverses, and it starts to go up, and upward trend starts. This is a bit more steep compared to the previous year. We see quite some high peaks here as well in March, and then it sort of plateaus and moves horizontally before coming down, starting into a downward trend around October time. So both years have their idiosyncrasies, their particularities. They're not a complete photocopy of very similar plots. If you look at both years, 2012 seems a lot different to 11, which is good. Let's try to visualize it in a different manner. Here we have a scatter plot instead of a line plot. In the scatter plot, we need two axes or two features to be plotted against each other. So in this case, you can see the casual count against the total count. We could easily change that as well, and we will do after we've gone through this function call. So this is visualized using a scatter plot or the function scatter, which is part of pyplot. So plt.scatter. We give it an x-axis, which is presented first, followed by the y-axis. So in this case, we have casual on the x-axis and CNT, which is the total count, on the y-axis. We're giving it some color, and we're plotting these real points. They're actually counts, so they're integer points. We're giving labels to the x and y axis as casual and count respectively, and we're calling plt.show, which we don't need to either because this is a Jupyter notebook. And you can see that we have the casual count against the count. What would be interesting here to see would be to change some of these columns and features and see what happens to the plots. We'll actually do it to both the line plot and the scatter plot, because we could plot humidity and temperature over here to see what's happening there as well. So let's go up and see what names we have in terms of float, temperature and a temperature, humidity, wind speed, casual, registered, and count. So let's, perhaps by way of analysis, we could compare casual riders against registered riders, which should be informative for the business. So let's say casual against, casual against registered. We'll keep it blue. Maybe we'll give it an alpha of 0.5 so that there's some transparency and we can see overlapping points clearer. Here we are. So now we're seeing casual riders on the x-axis, which goes from 0 to 3500, depending on what day you're looking at, and the total count, which should now be called registered. Casual against registered. Casual against registered. So we see that there is a clear formation of two clusters, we could roughly say, visually speaking. A more dense cluster, that is days where you have more registered riders compared to casual riders, and in this case you have the other sparse cluster, which is casual riders compared to registered. Now, is this insight or interpretation correct? No, because we haven't looked at or considered the range of the two axes. In this case, you can see that casual riders go up until about 3,500, whereas the registered riders are a lot more. They go up to about the double that number, to 7,000. So what we can do is actually lock these two axes and make sure that the range is such that we appreciate this better. Here we are. So now this both axes are going from 0 to 7,000, and we start to appreciate that there are a lot more registered users compared to casual. And as we can see, this has pushed to the left as well. We only go to about 3,500, and we clearly have 3,500, and we clearly have these two kind of this forking effect that we're seeing here. Another thing we could do would be to check temp against a temp, and if you recall well from the last lab, a temp was a feeling temperature or feels like temperature. In this case, maybe we can use a different color, and we'll refrain from setting the limit for now. We'll change the labels of our columns, so this is temp and feels like temp, and let's see what that looks like. So since there isn't a lot more difference, we see some jitter on this diagonal line. Essentially, it's a linear function. They are both correlated, highly tightly correlated, with some jitter happening at extreme temperatures. This has been scaled already. This is why we see values from 0.1 to 0.9 on both. There's a few outliers here which are interesting. So we could try to change the alpha to, let's say, 0.8 and see, sorry, the other way around, that makes this more translucent. We want to become more transparent. So 0.2, and we start to see more jitter, perhaps even 0.05, and we start to see that, of course, temperatures stay within a certain range, and the extremities have more jitter than the central core. Okay, let's try and plot a few of the columns on the line plot. The first thing we can look at is our temperature. So let's change that to temp, and the biker interval over time changes to temperature over time, date, and y number of y label becomes temperature, and so on and so forth. Let's run this. So temperature over time, temp goes from 0.1 to 0.9, and we start to see that there is a clear pattern here, which is sort of very similar in both years. Of course, there are some idiosyncrasies, and these are important. And this is the kind of particularity or nuance that will inform our machine learning model when we get to the modeling lab. Let's try and plot a temp in this plot as well. So let's put another plz.plot call, give it a temp, call it feels like temp, temperature, temperatures over time, y label stays the same, and we run it. Now we see perhaps it might be a good idea to add a bit of transparency. Let's add alpha at 0.5, and we start to appreciate how between October or November 2011 and April 2012, both of these temperature scales were very much correlated. And this tends to happen in the winter period. All of these 2 years clearly or visibly anyway. Whereas in the summer, our feels like temperature sometimes has had or once at least, has had a really significant drop in the summer of 2012. But in any case, in the summer months, we see that the feels like temperature is a bit lower compared to the temperature reading. And this could be because of the wind chill effect or perhaps humidity, but we have to look at that. Perhaps it's a good idea to put humidity in this plot as well, or maybe I can just type it out. So data humidity, label humidity alpha 0.3 or 5 is good enough. And let's see, there we are. So perhaps it's a good idea to change our alpha readings and see what's happening. Okay, humidity has fallen a little bit, but the spike is still unexplained, at least now in our very preliminary, rudimentary analysis or investigation. But this will start to become clearer. Perhaps a good idea would be to plot temp against humidity as well. Sorry, the name of that column is hum. So we can't really see any pattern other than a very random sort of noise spread all over the place. Let's see what else we could plot. Weather situation, temp. Wind speed is it's another one we could use. Let's maybe just replace wind speed here so as not to clutter the plot. Wind speed, and I'm gonna keep all of the rest here. Again, okay, interesting. Still, we don't really see much. Let's see if we can see anything here, which probably is not going to be the case. Yeah. Okay, let's move on and see another type of visualization we can do where we start to look at all of these columns now. It'd be a good idea to see the distribution in terms of their histograms and their KDEs. So what we do here is we start to use Seaborn, and Seaborn has been imported as SNS. So we set the style as a dark grid. Let's change that to a white grid so that you can see and appreciate the difference. Because the dataset has numerical as well as object and other types of columns, we want to use the select_d_types function from the data frame, which is stored in data, and this is a function in pandas. We include only int64 and float64 columns, thereby storing these columns into numerical_columns. We can confirm that by printing numerical columns here, and let's for a moment delete this. So here we see the index for all of the columns that are stored in numerical columns. It's giving us all of the columns in the dataset that has either the type int64 or float64. We'll also change this to say object, and we'll see DTE day, because we remember this is an object data type. Remember, we also did date time, so we might not see it because that's our index, and that is the case. The index is temp, atemp, hum, and wind speed, so it's not selecting our date time data set. But if we were to say data dot reset index, which is going to reset the index and bring the index date time index back into the columns list, then we shall see date time appearing as one of the columns. So let's undo all of this and go back to what we were doing. Okay, so now that we have numerical columns, the names of numerical columns in an index, we plot the distribution of each numerical feature by calling plt.figure. Fig size, we give it some fig size, which is going to be the 3 times the length of numerical columns. So it's essentially going to be long enough to include in it all of these multiple subplots. So for index and feature in enumerate function, which is going to take numerical columns, it's going to give us an output which is an index, so 1 2 3 4 5, and then the feature, which is the actual name of that column. So when we do a subplot call on PLT, we provided the len numerical columns and then 2. So this is 2 columns in that plot, and this will be the number of rows in that plot. We give it the index to say plot it in that particular position, call a hist plot, which is going to draw a histogram, give it the feature, which is that particular column name, and call it using data so that it's going to pull that data. We give it the kernel density estimator as true, because we not only do we want to draw the histogram but also overlay the density function to be able to see that curve. For now we can set it as false so that we can only see the histogram, and we'll rerun it to include the KDE. We give it some title to the name of that feature. We calculate the skewness of that particular feature by calling data features. This is the actual data in that array or column. Or you can call the skew function, which is going to give us the skew on that, round it up and include it as this label for skewness. PLT.show is again not required. So what we can do is delete all of this and see what impact it has. So if you recall, we changed white grid from dark grid, and that's why the background color of each subplot has been changed from grayish to white. We can change that to dark just so we have a bit of contrast in the next run. You remember the numerical columns, we add the numerical columns, we created the list or the figure by calling plt.figure, giving it a figure size of 14, which is the length. We can change that so that you'll see the impact. Let's say 10, so it'll be a bit narrower. And then we're plotting each of those subplots one by one in a for loop using the enumerate function, which is giving us some kind of a counter, and the actual column name, which is going to be pulled out and visualized and plotted. We use histoplot, which is putting the histogram, and we set KDE false, so this time I'm just going to set it to true, and then we'll see an overlaid KDE in each of the subplots. And then we give it a title so that we know what column or feature we're looking at and what skewness it has in there. So let's rerun it, and then we'll start to explain each of these subplots. So as you can see, because I got rid of the tight underscore layout, we have some overlap happening here. Let's put that back here, plt dot type underscore layout, and we run it again. Okay, so now we see that the pyplot is already taking care of the spaces and ensuring that no overlap happens here. This is a good way to make sure that the visualizations come out neat. And you see that the width has reduced as well. If I reduce it to, let's say, 6, you will see even narrower plot, as you can see here. If I change this from the length of numerical columns, whatever it might be, 8 or 7, I think, or 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15, so that's 15 multiplied by 3. Let's say if we do it 2, what happens then? Plots have become a lot tighter and smaller. Let's say if I change this and just take the length of numerical columns, which is 15, and the width is 6, what happens then? Okay, so it's very band-like and almost very difficult to interpret. So that's why we want to give it a bit more room. We can change this back to, let's say, 10, and this was 15. Still not good enough. Perhaps we double this, so the length is 15, and that's 30. Sorry, 2. So that's 15 into 2, 30. This is a bit better. If we do 3, 15 into 3, 45, that's giving us the original one, if I recall well. Perhaps this was 14. Yeah, so this is where we began, I believe. And just as a test, we remove the length numerical column into 3 and replace it with 45, which I believe is going to be an exact copy of what we already see. Yeah. So it's just a way to give it some generic or dynamic code so that it adapts to the number of columns being passed. All right, so let's look at what the plots tell us. Let's ignore instant because this is just a counter. Skewness of season is also 0 because this is again quite a distinct categorical feature. Skewness of year is also not much informative because there's just 2 years, as we know. Months we know that go from 1 to 12. We can see that actually there are multiple Decembers here. Perhaps we have a third December that is from a third year. Skewness in holidays also not very informative, but if we keep scrolling down and start looking at the float columns, we start to see a bit more interesting patterns that emerge. So for temperature, we can start to see bimodality, 2 peaks happening around 0.3 and 0.7. So this shows the 2 seasons, perhaps summer and winter, again with a temperature as well. So the higher temperatures are a bit more peaky compared to temp, and the lower temperatures in a temp are a bit decreased compared to temp as well. With humidity, we see a unimodal distribution centering almost around 0.6 or thereabouts. With wind speed, we see a bit of a tail on the distribution. We see the distribution as sort of a mean around 0.15, 0.16, and has a bit of a long tail, which is some outliers that were quite windy days. With casual and registered riders of bikes, we see quite a bit of variance in here. Long tails, some days that are going up to 3,500 renters or users in casual renting. And we see some peaks in the beginning, which is quite understandable, because most users or most days see a lower number of renters as opposed to registered. When there's a registered usage of the bike, we see that already this is a unimodal distribution. It is showing that there are regular and consistent users of bikes that are registered with this company and are regularly taking the bikes perhaps to work or to commute in the city. And this has stayed quite consistent. The mean is just below 4,000. And finally, the overall count, when you look at the registered and the casual users, you see a distribution that has the presentation of the registered renters of the bikes with some idiosyncrasies being introduced by the casual usage. So let's start to look at Seaborn for a scatter plot that's a bit more nuanced and detailed and more encompassing of multiple features. So we use the function called swarm plot using Seaborn, sns.swarmplot. We plot this within a plt.figure, giving it a particular size that we want to see, and then we give it the x and y axes as casual and count, casual users against all users. We use hue or color or to color the markers using season, so there'll be 4 colors. We give it the data frame, so data is equal to our data variable, which is the data frame we loaded our data into, and the palette, which is this particular palette. We can change this, or we can just use the default by ignoring it, and then give it some title to our plot, which is bike rentals by season, x label and y label, telling us what features we're plotting on the x and y. So if we run this, we have a couple of warnings. So the first one says 50% of the points cannot be placed. You may want to decrease the size of the markers or use strip plot. The second warning tells us 33.3% of the points cannot be placed. You may want to decrease the size of the markers or use strip plot. Okay, let's take a look at it first and then we'll go back and deal with that warning. So because it's a bit dark and not very appealing in its color, I'm going to rerun it and load the palette so that it's a bit more lively in color. So here we are. So on the x-axis we have casual usage, and on the y-axis we have total count. We have 4 seasons, and we can see that there is seasonal change, and really bike usage tends to be more in the green and the yellow compared to the black, which is more centered in the lower part of this plot, with some outliers, of course, going up. And then again, the second season is dark green, so we're not really sure where the dark green and the light green overlap is. Perhaps we can introduce an alpha setting here. Here we are. Still, we don't really have great visibility. Let's change that to bright. Okay, so now we have oranges and reds. Now, we know that only 50% or 33% of these points have been plotted, so we're not really making an interpretation on all of the 731 points. And this is very important for us to fix. So let's try and fix this following the warnings that have been given us and the suggestions as well. So let's change the swarm plot to strip plot. So as we can see, the warning's gone, and we have the entirety of the points plotted here. So the difference between a swarm plot and a strip plot is that swarm plot adds a bit of a jitter to the plot for overlapping points. And we are better off using the strip plot in this case. There's no warnings or errors, and we can see the plot well and good. I think our initial observations still hold. Green's cluster seems to be high usage, with the orange, red a bit lower than that, and blue days are the lowest. So blue season, whatever that might be, perhaps it's a very cold season. We can check that by plotting this against temperature. So let's use casual and change that to temp, and we will see what's happening to the bike usage and renting on temperature. So we see when the temperatures are low, it's season 1. When temperatures are quite high or the highest, so summer, is season green, so most people use it then. The orange and red are spanning all seasons or all temperatures, most of the range of the temperatures. So I'm assuming this is giving us spring and autumn or fall. Okay, so let's move to the final two parts of our lab today. Final two visualization types: pair plot and heat map. In pair plot, we're essentially going to be looking at all of the scatter matrix for the entire data frame. So each feature is plotted against the other, and we start to see a scatter plot for each of those pairs, and where the diagonal is, that's where we see a histogram, which is exactly the feature plotted against itself. And this might not be very visually appealing or informative, but at times, if you do want to look at all of the pairs in your data frame and they are a manageable number, it doesn't hurt to see some patterns, as we can see that are emerging here. So this is registered against registered and count, and these are mirror images. We can ignore. We already checked the casual against the registered. This seems interesting, which is temperature and a temp against instant. Oh, that's not interesting at all. That's just record index. All right. We use this function very simply. Use the pair plot function in Seaborn, sns.pairplot, and give it our data frame. It will create the pair plot automatically. We give it a super title to the entire plot calling pair plots for data frame, which appears here. You can even get rid of this for now. And there's a warning says the figure layout has changed to tight. But I'll leave this for you as homework to see how to get rid of this user warning when you try to run this. So that brings us to the final visualization of the day. So here we have a heat map, and for us to do this we need to do some kind of correlation. So what we do is we call SNS or heat map. That's a heat map function of Seaborn. We give it our data frame and we give it only numerical columns so that we can take out a Pearson's correlation, which is available in pandas. So we can simply just call the data frame and then the relevant columns, followed by a dot core CORR, which gives us a correlation matrix. We say that the annotation is true. Format is that we want 2 decimal places in the floating point precision. The line width is 2 and the color map is pastel 2, which I've commented out for now. We give it some title and we run it. So what it does is takes all numerical columns from instant through to count. It gives us some value between -1 and 0.1, -1 and 1, sorry. So we don't actually have a totally or a very high negative correlation, but we do have a very high positive correlation, and that's each column against itself, which is really meaningless or not very informative. However, we can see that the light orange is a very high correlation, and we can try and see if we see any 0.8s. We don't see any 0.8s. 0.8, here you go, 0.83. Perhaps that's the highest. No, 0.95. So registered and count have a 0.95 correlation. They're very, very highly positively correlated. Let's see a negative 0.52 between working day and casual. So if it's not a working day, we see more casual riders. That makes sense as well. Another one here, working day, casual is the same as a mirror image, so we ignore that. Minus 0.25, so a weak correlation between a working day and a holiday. That's also commonsensical. We can change the color map, so let's uncomment the C map and give it pastel 2. Perhaps it'll give us a more visually appealing heat map. We can change the annotation to false, and this will actually remove the labels from each of the boxes. You can remove line widths so that the white lines that you see between each of the squares will disappear. Here, if we change this to bright and bring back annotation, perhaps we can be a bit more, sorry, it's bright pastel 2, or let's just remove it altogether. Let's see what happens here. Yeah, that's all. The default color map, and we don't have any line widths here. We do have the annotation or labeling of each of the squares or boxes, the intersection of each of the pair of features, and we have the legend giving us an indication of the correlation. Of course, you could change the correlation coefficient by giving it a different name. In this case, perhaps name is Pearson. Name is the wrong one. Perhaps it's method. Yeah, so method is Pearson. We could also say Spearman. Of course, this depends on what you're using. Because we're using numerical data, we should be sticking to Pearson's and not Spearman, but this is a conversation for another time on how to select correlation methods. But for now, it suffices to say that we can use the default one, which is also Pearson. If we just double check, so that's Pearson now, and if we remove it, it should be exactly the same. That brings us to the end of this lab, and I'll see you in the next one. Thanks a lot.